So hello, everyone. It's been a brief hiatus, so happy to say welcome back to DFI's Impact webinar. The webinar is hosted by DFI's Driven Pile Committee to highlight developments, current practices, and case studies focused on driven pile foundations. And if you have a topic that might benefit this group, please reach out and volunteer yourself, or even better, volunteer one of your colleagues to present at this webinar. My name is Travis Coleman. I work for GRL Engineers in our Chicago office. So here's the quick rules. Everyone will be muted during the presentation. If you have questions, please use the chat function, and I'll be monitoring that, and the Q&A will be at the end of Van's presentation. So today, I'm happy to welcome my colleague and friend, Van Komurka. In Van's long career, he's extensively published and presented on characterizing and incorporating soil setup in the design of driven piles, optimizing pile loads and pile foundation selection, and evaluating load tests with the incremental rigidity method. So with that, Van, it is yours.
Thanks, Travis. I appreciated you calling me a friend. That's nice. Well, welcome, everyone. Thank you very much for attending. I'd like to thank DFI for inviting me to present. It's an honor and a privilege to be able to speak to you this morning, and thank you all for attending. If you didn't attend, it wouldn't really be a webinar. I'm hoping that you get something out of this, and maybe not everything sinks in. We'll cover a lot of material, but hopefully there will be some aspects that you'll find valuable. And I'll say this at the beginning in case some of you have to drop off. Please consider me as a resource. My email is on the screen now. My phone number will be at the end of the presentation and therefore in your slide packet. Feel free to call me, email me, discuss, brainstorm, whatever you want on this topic. This is a topic of very pet interest of mine. I'd be happy to discuss offline, either questions about this webinar right after, shortly after, or upcoming projects, current projects. Please, again, use me as a resource. So let's jump in. Here's our talk outline. First, we'll look at the overview of setup. I'm not sure how everyone, how familiar everyone is with the mechanism, what setup is as a mechanism. And then we'll talk about how we determine setup, both how we estimate it and how the accuracy of some of those estimations are affected by how it's determined. We'll look at the time rate of setup, how fast it comes on after driving. And then we'll talk about, in the case history, we'll present a couple of case histories where we talk about shaft setup profile, and we'll see what that is, both in terms of unit shaft setup and cumulative shaft setup. We'll contrast that characterization of setup with setup ratio, which is what I think most people would probably be familiar with and maybe use or talk about in their own practice. We'll dive into the application of the setup characterization to installations with depth variable criteria, how to develop multiple allowable loads from a single test program, and then as a tool for you, maybe a convincer for you, and a tool for you and your clients, we'll talk about the cost effectiveness of incorporating setup so that you or your clients have some ammunition as to why it's valuable and worthwhile to characterize and incorporate setup. So let's first look at the definition of setup and some of the mechanisms associated with it. So for those of you who may not be familiar, setup is a time-dependent soil resistance or capacity increase after driving a driven pile. Often we say the pile sets up after driving. The pile doesn't set up, the soil does, but it's kind of an interchangeable term, pile setup, soil setup. It's predominantly related to an increase in shaft resistance after excess core pressures that have been developed during driving dissipate. There are other mechanisms involved. We won't get into that, but if you think of it in broad, general, most likely or most common terms, it's related to dissipation of excess core pressures that are developed during driving. It's a very complex phenomenon. It's related to the pile, and it's related to a whole host of soil properties. I've even come to believe it's related to how the pile is driven, whether it's driven with a large hammer and large sets per blow or a small hammer and small sets per blow. So there are lots of factors that go into how setup is developed, what makes it happen and affects it. For those reasons, then, empirical relationships are limited in applicability. They aren't universally applicable. They have to be, by nature, conservative and have a large safety factor built in. And so, given that, site-specific test programs with given soil types to be tested in the soil conditions at a given site are the most valuable way to characterize setup. You can't look at a soil boring, you can't take constitutive soil properties, and get a real accurate estimate of setup. So really, test programs are the best way to go about it. We're going to see that setup can contribute a lot to a long-term pile capacity. And that's where the economy comes in. That's where it really shouldn't be ignored and it should be tested for and incorporated in design. So if you characterize setup and incorporate it into design and installation, you can use smaller hammers, you can install smaller pile sections, drive shorter piles, which means a reduced driving schedule, or for a given depth, you can obtain higher capacities and allowable loads. By the way, I'll speak and present in terms of allowable stress design terminology, capacities, allowable loads, safety factors. All these concepts are applicable to LRFD as well, but just for ease, we'll just talk in ASD terms. So all of those benefits then result in more economical installations. We talk about setup and test programs in, improving or reducing cost, risk, and schedule. So we're going to look at how we characterize cumulative shaft setup, and we'll see what that is. But the benefits of that go beyond simply a setup ratio. You can develop depth variable criteria. You can develop criteria for multiple allowable loads. After the test program, you can evaluate multiple hammer selection, pile sections, capacities, depths of driving. One of the benefits of this approach is that you can apply different safety factors to the initial capacity and to setup, and we'll talk about that a little more. And it allows you the flexibility to assign reduced capacities to piles that stop short or get damaged, and we'll see the effect of that. As well, as it says here, it may mean that you don't have to drive additional piles for replacement. So let's look at the different ways that setup can be estimated, depending on what you want to characterize, what components of setup you want to characterize, and how those need to be tested for. If you're just looking for setup magnitude, how much did a pile or how much did the soil set up? Total magnitude. Then you simply need an initial capacity at end of drive and some total capacity at some time after driving. And all that is then is just the pile changed this much capacity. Not very flexible or applicable in design and installation. That's the simplest way, the simplest characterization for setup. A better way to do it is to break out how much the shaft set up. And that's really where the setup occurs. Some setup occurs at the toe, but it's generally so small, small contribution to the overall pile capacity, it's not worth characterizing. So we generally ignore toe setup, although it's often there, but small. So you can break out just the setup on the shaft by looking at some initial shaft capacity. And in order to do that, you really need to do dynamic monitoring with some kind of signal matching. That's the only way you can separate shaft from toe during initial drive. And then again, at some time after driving, you have to separate shaft from toe, which during restrike, that is, separate shaft from toe resistance, which you can do with dynamic monitoring or with a static load test if you instrument it for load transfer response. And what that means is install strain gauges so that you can separate the shaft from the toe, at least one strain gauge near the toe. A more useful way to do it is to generate or to determine a setup profile. In other words, not only do you learn how much the shaft set up, but where along the shaft the soil gain capacity are set up. So you need an end of drive shaft resistance distribution, which you get from dynamic monitoring with signal matching, and you need a shaft resistance distribution at some restrike time later. Again, dynamic testing with signal matching or an instrumented static load test with strain gauges. And you can see that the difference between these efforts and these efforts isn't that much. In fact, they're virtually identical. So you may as well generate a shaft setup profile and cumulative, or profile both unit and cumulative, rather than just breaking out the shaft, figure out as well where along the shaft that setup is occurring. It's just as easy to do. And if you want time rate of setup, then you need capacity at multiple times after end of driving. And we'll look at time rate and how setup responds to time rate as well. So again, you need the total or the capacity during end of drive, and then at multiple restrike times after driving, and that will give you a time rate response or relationship. So let's look at the accuracy of how we determine, or the various accuracies that might be determined in characterizing setup. So first, what would I say? Make an analogy with a static load test. We'll transition or segue into how this is analogous to dynamic testing and a hammer. But first, everyone, I think, can wrap their heads and understand these concepts with respect to a static load test. So when the jack applies a test load during a static load test, the question is, what capacity is determined if you're during a static load test and the jack applies the test load, what capacity is determined if, and these are going to seem simplistic, but they'll lead into our I think, a better understanding of what we're going to talk about next. What capacity is determined if the reaction system pulls out of the ground? Well, I think that's pretty clear, right? The reaction system capacity. What capacity is determined if the pile deforms? That is, it buckles or something like that. Well, now you've determined the structural capacity of the pile. What if the pile plunges, geotechnically plunges, moves down into the ground without being able to accept more load? Now you've determined the pile's geotechnical capacity. And here's the one that we're interested in. What capacity is determined if the jack is maxed out? You've reached the jack's capacity. Well, I just gave the answer away. The jack is maxed out before the reaction system pulls out of the ground, or before the pile deforms, or before the pile plunges. What you've done in that case is determine the capacity of the jack. That's all you've done in maxing out the jack, having it reached its limit. Because the pile isn't moving. The pile still has resistance that the jack hasn't been able to mobilize. So all you're evidencing is the jack capacity. Okay, that seems simple and straightforward. So let's then segue and apply that to when you're driving a pile and the hammer applies a test load. All right. So what capacity is determined if the hammer is driving the pile and the pile deforms? Well, you've determined the pile's structural capacity. What if the pile is advancing through the soil? Well, you're failing the pile geotechnically, failing it, plunging it. So you're determining a pile's capacity. What if the driving terminates? You've stopped moving the pile, as in the case of a static load test where the jack is maxed out. The pile isn't moving. The pile is resisting everything the jack can put on it. In this case, driving terminates, practical refusal. The pile is resisting everything the hammer can put into it. Therefore, what you're testing at practical refusal is, or you're determining at practical refusal, is the hammer's capacity or its transferred impact force. But what you're learning about at practical refusal isn't the pile's geotechnical capacity. At practical refusal, you're learning about the hammer's capacity. So keep that in mind as we go forward. So in terms of the accuracy scenarios, the table you've already seen that we're going to get to next, if the blow count is too high, and we say here approximately 120 blows per foot, and the experienced person doing the signal matching should be able to give you an opinion, offer an opinion as to whether or not the pile is mobilizing all its capacity, or if indeed all you're measuring is the hammer's capacity. So if the blow count is too high, and we're going to use 120 blows per foot for that cutoff, the soil isn't failed. The capacity is not mobilized. Therefore, the geotechnical capacity of the pile is underestimated. So again, we had those previous two slides so that we can say that's analogous to a jack running out of capacity during a static load test. And the memory trigger here, or cue, that I like to use is when you're driving a pile, you have to move it to prove it. If you're not moving the pile, you're not mobilizing its capacity, you're not proving its capacity. you're not moving it. So you have to move it to prove it. Now, conversely, if the blow count is too low, and we're going to use 30 blows per foot as a cutoff here, again, that's a matter of judgment of an experienced person performing the signal matching. Now the soil pile system is moving so fast that dynamic measurement or dynamic analysis methods like wave equation or signal matching have trouble separating soil resistance from inertial effects. And so they tend to ascribe more capacity, more geotechnical capacity to the pile than it actually has. And so the capacity in that case, when the blow counts are too low, the capacity is overestimated. So now we get to this table, which wouldn't have been as easy to explain without those previous slides. So on the vertical axis, we have end of initial drive capacity and three categories. Either the blow counts are greater than 120, therefore the initial capacity is underestimated. They're in the blow counts at end of drive are in a reasonable range. They're between 30 and 120. Therefore, the pile capacity is reasonably estimated. Or the blow counts are less than 30, and therefore the initial pile capacity is potentially overestimated. And long-term capacity, that is during restrike, we have the same three categories. Either blow counts are too high, the restrike capacity is underestimated, they're in a reasonable range, the restrike capacity is reasonably estimated, or the blow counts are too low on restrike and the restrike capacity is potentially overestimated. And so given these nine potential combinations, if you look at these, there's only one box out of 9. There's only one combination of end of drive blow count range and restrike blow count range that reasonably estimates setup. And this is key when you're selecting a hammer to drive the test piles, when you're selecting a blow count at which to stop driving the test piles. It's harder when you're doing restrikes because you're not sure how much setup you're going to get. So to choose a hammer that puts your blow count between 30 and 120 during restrike is an art, if you will. It should be carefully thought out. If you have a test program with multiple pile types or sections or depths, again, this is key. Choosing initial blow counts in a reasonable range and restrike blow counts in a reasonable range is very important to getting reasonable setup results. So we've talked about magnitude of setup. Let's talk a little bit about time rate of setup. So on this plot, on the vertical axis, we have shafts set up in tons, and on the horizontal axis, we have time rate or time since end of initial drive, time since installation in days. And so this is a straight plot. The x-axis is straight algebra, straight axis. And you can see that that's the shape of the curve shows that there's a lot of setup that comes on early, and then it tapers off. It's a law of diminishing returns with respect to time and setup coming on a pile. This illustrates the point that setup is kind of front-end loaded, but it's not very valuable in getting a few points across. So let's look at this a little differently. Now on the vertical axis, we still have shaft setup in tons, but on the horizontal axis, now we've taken time since end of drive or time since installation, and we've put that in terms of log scale. And this is idealized. It's a schematic, it's idealized, but it's generally accepted that, again, if the setup mechanism is predominantly dissipation of excess pore pressures induced during driving, that setup occurs in a linear rate with respect to log time, because it becomes a soil consolidation issue. It's just like soil consolidation because excess pore pressures are dissipating. So once we realize this, there's several things that we can learn and instill in ourselves and our clients as we talk about test programs and how setup responds, behaves in the natural world due to this log relationship, and how we can then kind of structure our test programs. So if we look at this, 0.1 days is 2.5 hours, just in round numbers. It's actually 2.4, but say 2.5 hours. And here we have 1 day. So this first log cycle is 21.5 days, all right? So in that first log cycle, for this idealized linear relationship, setup with respect to the log of time. We're saying that a pile may set up 60 tons. Now, I'll give you a second to think about it. How long does it take that pile to set up the next 60 tons, to gain another 60 tons beyond that? How long does it take? And I'm hoping that you're saying, well, it's the next log cycle. So it's from 1 to 10 days. So that's 9 days. So in the first 21 and a half hours, it gains 60 tons. And to gain 60 tons again, another 60 tons, an additional 60 tons, it takes an additional 9 days. So now seeing that, we'd ask, well, how long does it take to gain an additional 60 tons? And the answer is another log cycle, 10 to 100 days. So 90 days. It takes 90 days to gain the next 60 tons. So if we look at where this plot ends, this particular pile and its setup relationship gained 120 tons in the first 10 days. And then in the next 50 days after that, it only gained 47 tons. So this illustrates, I think, in a more accessible or understandable way how front-end loaded the setup is. Now, there's two sides to this coin when we're looking at this. Number one, if the resistance is, oh, we don't have time to test for setup. Well, it comes on so fast, so early, that even short setup times, even short times to restrike, can yield significant setup results. In other words, if you drive on a Friday morning, let the pile sit over the weekend and come back and restrike it on Monday, that's 3 days. So here we are, here's 3 days here. And look, we're up here about 90 tons. I mean, that's not insignificant. So even short-term restrikes can yield reasonable and valuable setup magnitudes. The other side of that coin is if someone says, well, we want to test for a lot of setup, let's wait 60 days, even 40 days. Well, we all know what that does to construction schedules, and it adds for cost as well as schedule. Maybe the contractor has to demobilize and remobilize. So you can look at this and say, we really don't gain that much if we can restrike at say 10 days or even 3 days. We don't gain that much by waiting another 30 days. It doesn't, the payoff diminishes with respect to what it costs to wait that time. So knowing those two things helps us plan our timing for the setup. We always get asked, how long should we wait to set up or to restrike, to characterize setup? And it depends on a lot of things, mostly site constraints and schedule. I always tell clients, the longer you wait, the more setup you get, but waiting too long isn't worth it. So let's look at how we characterize shaft setup profiles. And we'll do that with a case history. And first we'll look at unit shaft setup profile, and then we'll look at cumulative shaft setup profile. So we'll present this as a case history, and this case history involves this building right here. And you can see that this is an artist's rendering. And so for you case history purists, I need to give you the disclaimer that this building was never built. The project did not go forward. We completed the test program for it. We were ready to provide recommendations. We evaluated everything fully, wrote a report, but the program didn't go forward. So I believe that the results are valid. It was just never built. And you can see that it's very long and thin. And so it had a large wind load on it. Now this is a picture of the foundation, and these numbers are too small to read, so don't worry about that. But long, thin foundation, and the numbers as we get closer, the neutral axes, of course, are through the middle here. And as we get further from the neutral axes, the loads on the foundations get higher. So the numbers go from a cool blue to a hot red, indicating an increase in required pile allowable loads from about, you won't be able to read these numbers, but from 176 or so in the middle here is what the structural engineer was looking to develop 7 different allowable pile loads for this project. From 174 or so in the middle out to 315 tons at the corners. And without being able to develop these high allowable loads, there wasn't physically room to drive enough piles beneath this building to support it. So this was a case where the results of the test program and developing very high allowable loads actually would make or break the project. It turned out not to be that way. It didn't go forward for other reasons, but it was one case where the geotechnical aspects really drove a lot of the project, and it was very rewarding to work on this and develop the high allowable loads recommendations. Generalized soil profile beneath the building. We'll look at these generalized soil types again: cohesive, fine grained, cohesionless, silts and sands. These are silty clays up here. We get into some clays again, and then down here, these are granular. These are tills, glacial tills, and you can see the blow counts aren't that stellar. Standard penetration blow counts. Down here at 105, we had a layer of fine to coarse sand that the blow counts jumped up, and we'll see the effect of that layer later in our results. Again, not very high blow counts until we get down to this till layer. And the unconfined compressive strengths of the clays aren't that stellar. All right, nothing out of the ordinary until, again, we get down near the till layer, and then we get some higher unconfined compressive strengths. But nothing that you look at and say, wow, this is an unusual site. Keep in mind these fine-grained cohesionless. We're going to see how the setup is affected in those soils, which aren't often given credit for setting up. So because we needed a range of allowable loads on this project, we considered 3 different closed-end pipe pile sections: 12 3/4 by 375, 14-inch by 0.5, and 16 by 0.5. We did a test program, tested those a number of those piles dynamically at end of drive and at restrike, performed CAPWAPS, a signal matching program, on both the end of drive and the beginning of restrike data. And we had an instrumented static load test, instrumented with strain gauges to determine load transfer response. That was the test program. 7 test piles of those various diameters. 1 was statically load tested. That was a 16-inch. Hammer used to install was a Delmag D46, 172 foot kips manufacturer's rated energy. On restrike, because the piles would have set up and would have to mobilize more resistance than that hammer was capable of on restrike, we mobilized a GRL Apple drop hammer configured with a 20-ton ram that had a drop height and ram combination that gave it a potential to mobilize 388 foot kips of transferred energy. Embedded lengths of the test piles range from 116 to 147. And end of drive penetration resistances, not that much, 29 to 69. Again, not driving the piles real hard, not driving the piles all that deep. Pretty typical, or I should say, not outside the range of normalcy for pile driving. This is a picture of the test setup. The existing building is here. This building was going to be raised, and so for our initial portion of the test program, we only had access to the sidewalk. We'll see more pictures of that, but that's where the static load test cluster was driven. Here's the static load test cluster. We've seen this picture before, and you can kind of make out the different pile diameters. Here's a 16. You can see this is a 14, a little bit smaller. 12 3/4 over here, a little bit smaller, and our static load test pile is in the middle. So this was our static load test setup for the project. So presenting the driving response, on the vertical axis, we have pile toe elevation. So these 3 schematics here are just here to indicate that these values are plotted as the pile goes deeper. The pile toe is going deeper, and this is the penetration resistance at those various toe elevations. That's all that's intending to show there. So not too high of blow counts. We're at 10 to 15 blows down to that. Remember that hard layer we saw at negative 105 for that hard layer of fine sand. Drive through that, and then it's somewhat layered below that until we get down to the till. Now, these are penetration resistance blows per foot. The Delmag that we were using was a variable stroke hammer. So these blows aren't really indicative of capacity because or uniform driving response, because the stroke can vary. A better way to look at the driving response is with the case method initial drive capacity. So with the dynamic monitoring, the pile driving analyzer attached to each test pile, I should say, these are only 16-inch piles. We're just going to look at the 16-inch pile response. Even though we drove multiple diameters, we're just looking at how the 16s drove. The case method with the pile driving analyzer gives us an estimated capacity for every foot of driving. And so this is a more readily comparable or direct output, if you will, of the driving response rather than stroke. So here we have, again, on the vertical axis, pile toe elevation. On the horizontal axis, now we have initial capacity at those various toe elevations during driving. And you can see that, again, we hit that hard layer at minus 105, and the resistance that we have to overcome to get through that layer is as much as 350 tons. And then it drops off and it's, again, layered below that. But not much of a resistance to overcome above that, 100 tons for most of the driving depth down to that hard layer. Now, signal matching was performed on the end of drive dynamic monitoring results, and a representative end of drive blow, and then that signal matching gave us a unit shaft resistance profile. So now this is again elevation, but now the pile toes, and this schematic is intended to represent this, the pile toes are at the bottom of these plots. So the pile toe is all the way down here, and then the unit shaft resistance for that entire length of pile is plotted. And here's the pile toe for the green line. Again, unit shaft resistance above that plotted. Here's the toe for the red line, unit shaft resistance above that is plotted. So again, initial drive, end of initial drive, unit shaft resistance as a function of elevation. And you have to be looking at this going, who chose that horizontal scale? No one, I mean, that scale is way out of whack for the data that's being presented, right? Well, I confess I chose that horizontal scale. And here's why. Because this is an end of drive. Now, we went out and restruck the piles. This is a different project, picture of a different project. Obviously, it's not near a building. It's not on a sidewalk. But this is the GRL's Apple drop hammer. Again, configured with a large ram. It can be lifted to various heights and restrike a pile to mobilize greater capacities than is generally available or economical with a conventional pile driving hammer. So this is what the drop hammer that we use looked like. Picture from a different project, but this is a drop hammer that we use. So these are the unit shaft resistances on restrike. And you can see that now instead of on the order of 500 to 1,500 pounds per square foot at the most, we're out here at 5,500 to 6,500 PSF at the most. So significant unit shaft setup, significant unit resistance change during, well, 39 to 45 days. That was the setup time for these piles. And you'll see also how much setup is occurring within these fine-grained cohesionless soils. Fine silts and sands, soils that aren't always given credit for setting up. Again, you can't look at a soil type and say, yes, it's going to set up or no. My own personal theory about why these soils set up is that during driving, they become quick. They liquefy. And that's why it's easy to drive through them and they don't develop a lot of shaft resistance initially. And then those excess pore pressures dissipate and they become very dense. They reconsolidate underneath the overburden stress above them and create a lot of horizontal stresses and friction against the pile shaft. So again, these soils setting up quite a bit. Now, this is all fine and good. We've characterized both the initial drive shaft resistance profiles and the restrike shaft resistance profiles. But what we're really interested in is the setup, the change in those two setup profiles, or I'm sorry, shaft resistance profiles. So if we want to determine the unit shaft setup profile, we take the beginning of restrike, in other words, the long-term shaft resistances, and we subtract from them the initial unit shaft resistances. So again, here we have elevation. Pile toes are down here. This is elevation of the sides of the shaft. Unit shaft resistance at restrike or long-term unit shaft minus the unit shaft resistance at initial drive or initially. And the difference between those profiles then gives us unit shaft setup profiles. And you'll note that, again, now we have setup, not total shaft resistance, but set up on the order of 6,000 PSF out here. And you might look at, say, this unit setup profile and say, oh, this is dropping off. We're losing setup as we go through these deposits. Well, in the legend, after each pile is identified, there's two numbers plotted. The end of drive, and I apologize, this arrow doesn't quite line up. The end of drive penetration resistance blows per foot, and the restrike penetration resistance blows per foot. And you can see that the restrike penetration resistance on all these piles was 300 and equivalent penetration resistance of 384 blows per foot. Again, not mobilized. So the setup's going to be under predicted because the restrike is not mobilized. We didn't expect this much setup, and we didn't configure the hammer big enough, the drop hammer. So the last section or portion of the pile that gets mobilized during restrike is the lower portion. So our opinion was that these decreases in the lower portion of the pile are not a result of actual setup decrease, but of not being able to mobilize the lower portion of the pile, as evidenced by these higher restrike blow counts. So this is fine because it's a unit shaft setup. Now, if we take these unit shaft setups and starting at the ground surface, apply them to the side surface area of a 16-inch diameter pile, as we go deeper, we can apply those unit shaft setups to the side area and get a cumulative setup profile for each one of these test piles, and that's what this is. So now we're back to looking at pile toe elevation versus cumulative setup. So let's just look at the blue line. Again, that's the northwest anchor pile. We would expect that had we stopped that pile at an elevation of, these are hard to read for you, I understand, sorry. At an elevation of minus 80, we would have expected it to set up approximately 150 tons. And if we'd stopped at an elevation of minus 90, we would have expected it to set up approximately 300 tons, and so forth. And at its full depth, it's set up 750 tons. And again, we get that from applying these unit shaft resistances to the side, or unit setups, to the side area of the pile. So these are the three results from the three 16-inch test piles: cumulative shaft setup, full depth. And you notice that we didn't have to drive these piles to multiple depths to get a full depth setup profile. Drove it to one depth, toe down here, and we know we've characterized its setup response or behavior, full depth along its shaft. So then to choose for design, we take a design, well, there's two ways to do it, and we'll talk about it. One way to do it is to take a unit shaft setup design envelope, which is in the purple. So we're going to say for this project, we are going to use a unit shaft setup profile that looks like this. And that's one way to do it. And you can now ascribe these setup values to these various soil deposits, maybe for a database for future projects in the area. And again, if we take this design shaft setup envelope and apply it to a 16-inch pile side area. Oh, well, yeah, one more point to make here. So we are down, and again, we looked at these various setup profiles and looked at the blow counts and whether they were underpredicted or overpredicted to choose this 5,000 pounds per square foot setup below elevation minus 80. And to give you a sense of that and what that means is for a 16-inch diameter pile, this 5,000 PSF setup corresponds to 10 tons per linear foot of embedment. So for every foot below elevation minus 80, we expect the pile, we will design the pile to set up an additional 10 tons per linear foot after driving. So I hope that those of you who have worked with setup, have worked with pile design and magnitudes, have a sense of how much that is and what that can mean to long-term pile capacity and economics. So if we apply that design envelope, this purple line design envelope, to the side area of a 16-inch pile, we get this lower bound design cumulative shaft setup profile. So now this is pile toe elevation, and this is cumulative shaft setup. So this tells us, the purple line tells us, at any elevation, at any embedment depth, how much setup we can incorporate into our design. Now, we could have just chosen the blue line because it lower bounds all our other results. The purple line lower bounds that even more, so we're adding some conservatism to it. So not only have we not mobilized all the resistance and therefore underestimated the setup, we're using a lower bound setup profile even beyond that. So we're adding conservatism on top of conservatism. And we're still counting on, or we're still characterizing 700 tons of setup at the depths explored by the deepest test pile, 16-inch test pile. So what we can do with that is, here's the case method end of drive capacity profile. So now this is, again, toe elevation on the vertical axis, ultimate capacity on the horizontal axis. And we've seen this before in our driving response. Remember, this is again, these numbers are hard to read, I understand, sorry. This is 350 tons. Recall that was the maximum driving resistance that the pile had to overcome through that dense sand layer at minus 105. So this is the initial capacity profile. Here's our design setup profile. So if we add that together, remember, long-term capacity is initial plus setup. We add those two together, and we get this. The blue line is an estimated long-term capacity profile. Now, again, realize that what we've done here is characterize setup response, full depth, even though we only drove one pile to one depth. We drove more than one test pile, but what I'm saying is this is a result of all the test piles. We didn't have to drive the test piles to multiple depths. And we've estimated long-term capacity, including initial plus setup, full depth for the pile, even though we only drove it to a single depth. So I always kind of want to improve a test program when I hear someone say, well, we want to see how the piles set up or respond, or what kind of capacities we can get at different depths. Well, you don't have to do that. You can drive the pile as deep as you can, and we'll see that a little later in the next case history. And this lets you characterize its setup and long-term capacity response, full depth, even though you only drive one pile to one depth. So there's a couple three things to realize from this. One is that at least at this depth, setup is contributing 80% of the pile's long-term capacity. Driving through that layer initially, the pile had a resistance of 150 tons. And let's just say 40 days later, it had a resistance of 750 tons. So setup is adding 80%, or accounting for 80% of the pile's long-term capacity. So when we say setup can account for a lot of a pile's capacity, this is an example of that. Now, there's a couple other things to glean from this presentation. One is, if you get these results and a designer, design team, structural engineer, owner, whoever you're working with, says, boy, I'm not comfortable counting on 80% of my pile's capacity coming on after driving. It's not evidenced, based on a couple of test pile results, however many test pile results. It seems like we don't see it. It's just coming on. I'm uncomfortable with that. Okay, well, because you've separated the initial drive contribution and the setup contribution, you can apply different safety factors to those two long-term capacity components. The initial capacity is evidenced during driving. Site variability is going to be evidenced. Driven piles are tested piles. So the blow counts are going to evidence your initial capacity. If someone in the design team is not comfortable with this much setup, say, well, okay, say we cut this in half. Say you're going to design this pile to a factor of safety of 2, and you cut the setup in half. That's equivalent of applying a safety factor of 4 to the setup. You can adjust this design setup curve to whatever comfort level or safety factor you want, or the design team desires. By the way, there's a paper on GRL's website on how to apply different safety factors, separate safety factors to end of drive and setup components. So you can go to the GRL website to look at that paper if you want to learn more about that. The other thing to look at here is often when I suggest that we characterize setup or that someone can improve their practice in doing so, the answer I get is, well, we already incorporate setup. We just wait however many days to run our static load test. We wait 10 days to run our static load test, so it includes setup. So I want you to look at this full depth characterization of all these capacity components and think about if you simply run a static load test after a wait period, what information do you have? Do you gain? What do you know from this plot if you run a static load test at 40 days? And the answer is you get that point right there. And that's all. And that point right there is representative, corresponds to a given blow count and at a given depth. So if you go to design for that and you're driving your production piles and you get that blow count higher at a higher elevation, you get that blow count up here somewhere. Now you have your required initial capacity, but you don't have your required setup because you've got that blow count higher up in the profile. So how much deeper do you go to get the setup you need? You don't know. Conversely, if you drive to here, to that depth, and you get your blow and you get your setup, then you've reached your measured setup depth, but you don't have your blow count. Now you don't have your required initial capacity. So how much deeper do you need to go to get your initial capacity? Well, you're gaining setup all the while. You go deeper, but what blow count do you look for below that point? You don't know. So that is not nearly as valuable in applying criteria or driving piles or as economical as this characterization is. So a lot of times we hear talk about, let's contrast now what we've talked about so far in this approach and how we characterize setup so far this way with what we often hear about setup ratio, okay? And I'm sure that many of you are familiar with this. So setup ratio is defined as long-term capacity divided by initial, often. That's often the way it's done. We drove the pile, got an end of drive capacity from dynamic testing, and then we restruck it or we statically load tested it, and it carried twice the load. So the setup ratio was 2. Well, when you do that, if you determine it in terms of total capacity, both shaft and tow combined, it's very dependent on the tow contribution to that total capacity. We'll see that in examples. So if you're going to talk about setup ratio, the first thing you have to ask is have you taken the ratio of the total capacity or the ratio of just the setup capacity? In other words, have you separated out the shaft setup? And it's better to characterize a change in shaft capacity than in total capacity. But it's not very practical in applying that then to criteria. It's very practical in applying that setup ratio to discrete soil layers when you're doing a drivability analysis with the wave equation. But it's hard to apply it to criteria and especially on a variable site. We've been talking about setup and now we're characterizing setup ratio, but I just wanted to throw in here that there are cases where the tow relaxes and we can't ignore that. I don't want to leave that out of this, like the tow never relaxes and setup is magical and you get all kinds of great benefits from it. You do from setup, but you also have to take into account potential soil relaxation at the tow and in certain conditions. So don't ignore that. So let's look at how setup ratio can vary depending on end conditions. So here's our competent bearing material, and we're going to drive a pile and stop a few feet short of that. So we have 50 tons on the shaft, but not much on the tow, soft driving above this competent material. And then we let it set, we come back and restrike it, and now the shaft has set up 150 tons. And so long term, we now have 200 tons on the shaft. We still have 10 tons on the tow. So we calculate a setup ratio for that friction pile with a soft toe of 210, just 210, divided by initial, 60, and we get a setup ratio of 3.5. Now we drive a few feet deeper and we hit that hard bearing layer, that competent bearing material, and boom, the toe resistance jumps up to 100 tons. Shaft is still 50. We haven't put that much extra length to it to gain any more in the shaft. Shaft responds exactly the same, sets up 150 tons. Now we have 200 tons in the shaft, just like before, 100 tons on the toe. And now if we calculate our setup ratio, the ratio of long-term is 200 plus 100, divided by initial, 150, we get a setup ratio of 2. Well, the shaft responded exactly the same way in both cases. The shaft gained 150 tons in both cases. And yet, the difference in the toe responses at end of driving gave us 2 significantly different setup ratios. So again, it's better to look at what's happening on just the shaft, and then you don't have to worry about what's happening at the toe. And you won't get these kind of discrepancies depending on what your toe resistance, your toe condition. So let's look at our example again. Remember, setup ratio is Q long-term divided by Q initial. So for this example, we would take the blue curve, Q long-term, initial plus setup, and divide it by the red curve, divide it by initial. And if we do that for this soil profile, we get this setup ratio profile. And so if you're going to use a setup ratio in your design and somehow apply it to design, what setup ratio do you use? You have a variable site, your piles may be stopping at various depths, depending on how the site stratigraphy varies across your site footprint. Again, pile toe elevation versus setup ratio. So again, it just is, it's here to illustrate the difficulties and the uncertainties and the variability associated with setup ratio versus looking at the way we've already presented characterizing setup. So we've talked so far about characterizing setup, but we haven't talked about incorporating it into design, and we've talked about incorporating it into design. Let me go back one here, because I guess I didn't mention it, but it can be emphasized here. In order to, for driving this pile, the maximum driving resistance that has to overcome during driving at any depth in the profile is right here, 350 tons. So you can size your hammer and your pile section, the amount of steel or concrete in your pile, to overcome a maximum driving resistance of 300 tons. And yet available to the designer is 1,000 tons resistance, geotechnical resistance long-term. So that's a great benefit in terms of economy. You design the pile to be driven to 350 tons, you can figure that capacity, ultimate capacity, and you figure long-term it has an ultimate capacity of 1,000 tons. So that's where the design, if you will, comes in. So we've talked about incorporating setup, characterizing it, and incorporating it in design. Now let's talk about incorporating it into installation. Okay, great. We've characterized it this way, and we've hopefully demonstrated the benefits of characterizing it this way. Let's see now how we bring that into our driving criteria and our field installations. So we're going to take this design cumulative setup profile and use it to develop driving criteria. And again, we've mentioned this before, but at elevation, toe elevation minus 80, we'd expect about 160 tons of setup. At toe elevation minus 100, we'd expect about 400 tons of setup, and so forth. So that's kind of what we're using for design now to generate our driving criteria. So here's our driving criteria on how we would develop that. We're looking for 700 tons ultimate, say, maybe 350 tons allowable. And remember, we needed over 300 tons for this case history, for this long, thin building in the corner piles. So here we have pile toe elevation on the vertical axis, ultimate capacity on the horizontal axis. We're looking for 700 tons ultimate. So it doesn't matter what the pile toe elevation is, we need 700 tons. This is our target long-term ultimate capacity at all pile toe elevations. That's the red line, 700 tons. And this is our design setup profile that we got from our test program. Remember the purple line that we used for design. This is how we expect setup to come on the pile at various depths. So at an example toe elevation, just one pile toe elevation during driving, if we expect 250 tons to come on in setup, what do we need at initial driving? What do we need to evidence at that pile toe elevation if we want to stop the pile, if it's okay to stop the pile driving? And the answer is 100, 200, 300, 450 tons. So if we get down to this elevation and we're counting on 250 tons in setup, we need the evidence through our blow count during driving of 450 tons. Now at higher elevations, up here, if we're only getting 50, if we're at elevation, toe elevation minus 40, and we're only expecting 50 tons in setup, then we need the evidence during our driving, we need a blow count that corresponds to 650 tons initial. Conversely, if we go deeper, we go down to, oh, say here, and we expect 500 tons in setup. We're at this toe elevation now. We only need to evidence 200 tons during initial drive. So I'm hoping everyone kind of follows that, so that as you go deeper, your required initial decreases. It decreases from like this. If you can, I'm going just these swings of the cursor are getting less and less as the pile goes deeper and deeper, and we need to make up less and less to get our 700 from what we expect in setup. That's for a 700-ton ultimate target. Recall from our case history, we wanted multiple allowable loads. Well, okay. So now we want to generate criteria for a 600-ton ultimate pile. No matter what where the pile toe elevation stops, we need 600 tons long-term. Setup profile is the same. We expect the same setup response. Again, pile toe elevation versus ultimate capacity. We expect the same setup response with depth, regardless of what our target ultimate is. And so now at that same toe depth, if we expect 250 tons in setup, if we're looking for 600 tons ultimate, now we only need blow counts to evidence 100, 200, 350 tons at end of drive, a blow count equal to that. And so again, as the pile goes deeper, you get more and more setup on over here, and you need less and less at initial drive, until at some depth here, you would need literally zero initial capacity, because you would expect all your required ultimate to come on in setup. And I've had this conversation with structural engineers. They'll call and say, I have an inspector in the field, and I thought we were putting in high capacity piles, and he's telling me that he or she is telling me that we only need 10 blows a foot when we get down to a certain depth. That can't be right, is it? And I somewhat facetiously respond, yeah, that's right. And if he'd driven another 10 feet, he wouldn't need any blows at all. That usually precipitates a meeting. That doesn't placate anyone. But I mean, you can see that in this presentation, you can see how that comes about. So how do we develop criteria from that? Well, if we plot just the required initial, in other words, just the distance between either this red line for 700 tons, the distance between the setup and that red line, or the distance between the setup and the green line for 600 tons, if we plot just pile toe elevation versus required initial capacity, these are the plots we get. So what we do is we come into these plots at various toe elevations or embedment depths, determine our required initial capacities for these various allowable loads, and using a refined wave equation, which by the way is another benefit of running the test program, you can produce refined wave equations, generate the blow counts that are required to achieve or to evidence these required initial capacities that decrease with depth And so therefore the required blow counts decrease with depth. As you go deeper and more setup comes on, you need less initial capacity. So the result of that is a driving table that's provided the inspector like this. Now, this is a driving table that's been generated for a variable stroke, variable energy hammer. But if you had a single acting hammer like an air hammer or a fuel hydraulic hammer that you were going to put on one setting, this table would be one column. But let's just look at the 9-foot column. Now the setup was coming on very fast, so we're breaking down the depth intervals in 3 feet, because remember we were getting 5,000 psf per foot, or I'm sorry, 10 tons per foot at 5,000 psf, so 10 tons per foot of embedment. So we broke the elevation intervals for this table down fairly small, 3 feet, but these could be wider if you weren't getting as much setup per foot. So at 9 feet, say you're down at 99 feet, and you're driving along, and the inspector sees a 9-foot stroke, and you're at 99 feet, and the blow counts are 30. What do? You keep going. You don't have the required blow counts. And then you get down to 90 or 100 feet, and your blow counts jump up to 35. You still don't have it. And you get down to 101 feet, and your blow counts are at 38, and you still don't have it. So you drive another foot, you get down to 102, and now your blow counts are at 40, and you've gone a little bit deeper than this last criteria was required. You've gained a little more setup than was counted on here. And now at 40, your blow counts exceed the 36 required, and so you can stop driving the pile. I term this, it's an extremely elegant way to take into account both spatial site variability, and by spatial site variability, I mean like in plan view, XY plan view, and the depth variability of the way the setup response comes on a driven pile. Because as you move around a site, the piles will evidence changes in site stratigraphy, in plan variation, in spatial variation, because driven piles are tested piles. And you've developed a design setup profile that varies with depth, and therefore this takes into account that setup coming on with depth. And so it accounts for both spatial variability and of the driving response initially, and the depth variability of the setup response after the pile is driven. So you don't drive the piles any deeper than required. So let's look at a couple case histories here, a couple of cost effectiveness illustrations. The first one very simple, the second one a little bit more involved. So you've seen this enough. Here we are. Here's our results from one of the test piles. And say that you wanted to stop, you didn't want to characterize setup. And by the way, we're going to use a cost of $65 per foot for these installed 16-inch piles. You didn't want to characterize setup. Didn't have time, didn't think it was worth the money, didn't think the contribution would be significant enough to go after. So you're just going to drive and look at initial capacity. Here's the maximum initial capacity that we saw in the profile, 350 tons, 340, I think. Yeah, 340. If you stopped here and you didn't do any testing and applied a safety factor of 3, now I'm going to say this once, but it's going to apply to all the safety factors you see associated with the different construction control methods. These are representative safety factors just to give us some numbers and a range to do the math and to apply costs to. These aren't necessarily recommended safety factors for these various levels of construction monitoring. So don't ascribe these safety factors necessarily to the construction monitoring methods, just that they're there to give us a range so that we can put numbers and costs to the various ranges of safety factors. So again, we're starting with a 350 or 340 ton allowable. If we don't do any testing, we get an safety factor of 3 and allowable load of 113. Dynamic testing, safety factor 2.5, we get an allowable load of 136. Static testing, safety factor 2, we get an allowable load of 170. We won't go into a lot of detail on support cost. There's a paper on the GRL website that does go into detail on support cost. Support cost is defined as the cost of the installed pile, that is its cost per foot times its length, divided by its allowable load. So it's a measure of cost effectiveness, if you will. Installed cost, that is cost per foot times depth, divided by its allowable load. So here are the support costs, dollars per ton, for these various safety factors, if you will, if you don't use setup. If you do use setup at that same elevation, now you're bumped up to 780 tons. Yes, 780 tons. The non-testing option goes away down here. You can't characterize setup without doing testing. So we only are left with dynamic or static as our control method options. But again, assigning the same safety factors to them. Look at what the jump in allowable loads has done with safety factor or with setup incorporated, and look at how the decrease in support costs, dollars per ton in the ground, when you incorporate setup. So again, an evidence of the cost effectiveness of testing for setup. Now, one of the other advantages of looking at it this way is you might look at this and say, well, what if I want to use a really high allowable load down here? Is that more cost effective? Because I do get 1,000 tons ultimate, but I have to go deeper to get it. So does the added cost to install that depth make sense? Is it offset by the additional capacity that's generated? And this kind of shows, no, it's not. We'll look at this. I mean, you go quite a distance here. You invest a lot of pile length without gaining much capacity, and then you have to get a lot of capacity back to make up this invested cost right here. So even though this is now 1,010 ultimate tons, and you get these huge allowable loads, because of the extra length invested to go from 0.2 to 0.3, these two numbers are within accuracy virtually identical, and these two. So you could look at this and make an economic decision, make a cost decision, and say it's not worth going after these allowable loads. They're no more cost effective. In terms of the pile, we're not talking drive time or cap cost now. But in terms of the pile cost alone, it's not worth going after these allowable loads. You can look at this and say the invested length and extra cost does the extra capacity does not make up for the extra length and invested cost. So again, looking at it this way helps you make those kind of economic and allowable load choice decisions. This is a key point. I've most of my practice has been done with closed-end pipe backfilled with concrete because they're the most matched up, if you will. They take the most advantage of setup. This is key. Concrete filled pipe piles are the only pile type that can have their structural capacity changed after driving. Let me say that again. After driving, you can change the structural capacity of a concrete filled pipe pile, and it's the only pile type with which that's capable. So if we look at what's going on here, and this is both in terms of economics mostly, but remember, you design piles for two components, both two capacities, if you will, both structural and geotechnical. But often the structural is overlooked when a geotechnical is putting together a program. So with respect to capacity, initially, when you drive a closed-in pipe or the high displacement pile in a high setup environment, the initial capacity might be considered relatively low, and then over time, it sets up so that you have a relatively high geotechnical capacity long-term. Structurally, you can drive a relatively thin wall steel shell. It only has the steel in it, so it has a relatively low structural capacity initially. Then you backfill it with, I shouldn't say backfill, you fill it with concrete and change its structural capacity so that long-term, then the structural capacity is relatively high because now you have a steel and concrete composite section. So again, this is one of the benefits of a concrete filled pipe pile changing its structural capacity over time, the same way that it changes its geotechnical capacity over time with setup. And to give us a sense of the economy of that, if you will, if you derive the structural capacity from both steel and concrete, and this is a 4,000 psi mix, a 6,000 psi mix is not that big of a cost increment. It doesn't cost that much more to put in a higher strength concrete, so these numbers would even be more illustrative. And I'm told too that in some parts of the country, concrete is not considered inexpensive. Again, my practice is limited to the upper Midwest, and it is. So I'm presenting it this way. But if you have a 16-inch by half-inch pile, that's steel pile, it's backfilled with concrete, has an area steel of 24.3 inches. If you were to derive that same structural capacity from this section from steel alone, which is more expensive than this section, you would need 2.5 times the area steel to get the same structural capacity from this concrete filled pile. So that's where the economy comes into being able to fill that with concrete and increase its structural. Now, this is a fairly complex case history, and there's a paper we referenced at the end here on the GRL website of this. And so I'm not sure we're going to make all the points that are in this, but let's just look at this particular case history and the topics we're going to look at, give you a little bit of background, driving results, or the driving results from both the test program and production. We'll look at various safety factors associated with various construction control methods, and we'll look at the costs. Well, we'll look at these various construction control methods, safety factors, and cost schedule components, both with and without setup. And then we'll look at how whether we incorporate setup or not impacted the cost, or would impact the cost, schedule, and savings. So here's our profile. Again, nothing too stellar, nothing too different. Clays, undrained shear strengths 1,000 to 3,000. Fine grain granular, blow counts 15 to 30. Fine grain granular jumps up a little bit. The blow count's kind of a layered profile down here. And now here's our glacial till again with shear strengths that are pretty high, jumps up down here. This was a high-rise building. We knew the column loads were high, so we wanted to go after high allowable pile loads right away. Now, this is what was done. This is the way the project was built, is what we're talking about now. We're not showing options or alternatives. This is the way the building was designed and constructed. So, knowing that, we chose a 16-inch by half-inch steel pipe pile, concrete filled, and we used a Delmag D42 hammer to drive it, or 46 hammer to drive it. The 16-inch pile and this hammer were selected because they were commonly used in the area. The contractors knew how to handle them. They had cranes that could handle them. Nothing exorbitant or out of the ordinary with those selections. Test program consisted of 10 test piles, 5 indicator for reaction, 1 static load test pile with strain gauges, and it provided a good general site coverage. We drove the piles hard, both high blow counts and near their driving stress limits. And by the way, that's the most economical installation. The most economy in any driven pile installation is to drive a pile to near its driven stress limit, and then have that driven stress limit be near practical refusal blow count. That's the best way to install a pile in terms of economics. And then also to load it geotechnically to near its structural capacity. All those things, those 3 things add up to the most economical pile installation. All the test piles were dynamically monitored full depth. Aplapse or signal matching performed on end of drive. Beginning of restrike data. The restrikes were done with an apple drop hammer, 36 to 54 days after driving, and the apple drop hammer transferred up to 59 foot kits, 159 foot kits. So recall, long-term capacity. So now this is the testing, both the testing results and then the production driving results based on those testing results and the design based on them. Long-term capacity is initial plus setup. So what we got from the testing was driving the piles hard to near practical refusal, to near driving stress limits. We figured we could consistently mobilize 800 kips. Set up at anticipated embedment depths, maybe we should say at minimum anticipated embedment lengths, 400 kips. In other words, as short as any of the test piles drove, we saw at least 400 kips of setup. So 800 plus 400, we decided to design the piles for a long-term capacity of 1,200 kips based on the test program. Because we had an instrumented static load test, we applied a safety factor of 2. Therefore, allowable load was 600 kips or 300 tons on that 16-inch half pile. So production driving, 456 piles, 30,000 linear feet, an average of 66.5 feet per pile. Not a lot of footage in the ground to get 300 tons. Again, we'll see that the setup played a role in that. So when we talk about construction control methods now, as we move on to our next topic, that just means how have you determined when to stop driving the pile? Why do you know that you can stop driving it? What tells you that you have satisfactory blow counts? So that's what a construction control method is. So if we look at the alternative designs, depending on the construction control method, and again, we'll assign a range of safety factors more for illustrative purposes than to, we're not recommending that those particular safety factors be assigned, if you will, to those construction control methods. With setup, we have a long-term capacity of 1,200 kips. If we use a dynamic formula only and apply a safety factor of 3.5, we get disallowable load, wave equation, safety factor of 3, we get disallowable load, wave equation plus dynamic load testing. And again, we have to do this both at initial drive and restrike to characterize setup. Allowable load of 480. If we did wave equation, dynamic load testing, and a static load test applied a safety factor of 2, we'd get an allowable load of 600 kips. Similarly, if we don't incorporate setup, we only start with 800 kips, not 1,200. And so we get these allowable loads for the same range of safety factors. Cost, 51 per foot. And the construction management team was very cooperative in giving these costs. Concrete excavation, pile caps, or mat, different placement costs for the concrete. Construction control methods, in other words, from dynamic formula to what I would call a full boat test program with restrikes and instrumented static load tests. The range of those test program costs were $500 to $236,000. So the full boat testing program costs almost $250,000. And you're going to look at this and say, wow, that's a lot of testing cost. It is. So let's see if it's worth it. Driving productivity, 5.4 piles per calendar day. We're running up against the clock here, so I'm going to skip a little bit of the information that might be presented here. This gives us a sense of if we had not used setup, and we'll just talk about the full boat testing program here, the foundation cost would have been about $3.5 million. If we used setup, the total foundation cost, and these costs include the engineering, would have been about $2.5 million. So for the full boat testing program, including the $250,000 that it cost to perform the test program, setup saved $964,000 on the project, even including the cost of testing. I don't think we're going to go into these plots, just again for sake of time. There's a paper. This paper case history is also on the GRL website if you do want to dip into these a little bit further. So we've talked about cost and impact again, just to review. Even with a $250,000 test program, incorporating setup saved almost $1 million on the project piles. We talked about cost and schedule and risk as the 3 things that come out of a test program. So if we had designed and installed the piles without setup, and we started with an ultimate capacity of 800 kips, we would have had an allowable load of 400 kips and a driving duration of 127 days. Incorporating setup, the driving duration drops to 85 days. And so incorporating setup actually saves 42 days of driving schedule. Now, if you recall, the restrikes were performed anywhere from 36 to 54 days after driving. So the incorporating setup virtually saved enough driving schedule to pay, or to in schedule in terms of driving days, saved the production driving schedule saved as many days as the testing took. So again, when somebody says we don't have time for testing, you need to look closely at that and say, well, testing may save you time. I'm not going to go, well, just again, for time, know that we developed a method of incorporating the test program results, particularly the shaft setup profiles, cumulative shaft setup profiles, to assign damaged piles reduced capacities. And this kind of presents how that was done. And again, it's in more detail in the paper. But just know that because we had the test program results and because we characterized the setup the way we did, we had approximately 3% of the piles had a mortality rate of about 3%, which is a reasonable question if you're driving the piles to a high blow count and a high stress. 3% mortality. And because of the test program results, we were able to save 50% of the required replacement piles, which resulted in $70,000 of savings and 3 calendar days of schedule. So conclusions, we'll go through these fairly fast because I think we've emphasized them all the way. And again, looking at the clock, I apologize, we're a little long here. Long-term capacity, large contribution. We talked about all the benefits from incorporating setup, all result in more economy. Depth variable driving criteria for numerous allowable loads, even from a single test pile result. You can make economic hammer pile section size selection based on the results. And you can apply different safety factors to the end of drive and the setup capacity components, which is a benefit and a flexibility. Case history, the savings from the testing more than paid for the set testing. The savings for testing for setup alone, or just for setup, more than paid for the cost of testing for setup. The time it took, or the time in drive time saved, more than made up for the time it took to test for the setup. And again, here's a link to the paper, or at least again on GRL's website. There's a paper there. It's actually 2 papers there talking about this case history, and there's an article of a little bit lighter read in Pile Driving Magazine. So shout out to DFI and their Increased Testing Saves Money webinar series. This is a great case history to illustrate that. I will leave my telephone number, email up there again. I'll say again, use me as a resource, reach out, brainstorm, ask questions, discuss. We're happy to get involved in projects if you think any of these approaches can benefit you or your projects. So with that, I'll turn it back to, thank you for your attention, for your attendance and your attention. Hopefully, again, at least a few things were valuable. And I'll turn it back to Travis.
Thank you so much, Van. Hopefully all of us are utilizing setup, but I'm pretty certain that not all of us are giving it that much thought. And it's really valuable to think of setup with respect to the structural loads and the cost, especially, is probably something that a lot of us are not looking at all that closely, or the cost benefits that specifically. So thanks again, Van.
Well, thanks for having me.
If you have some questions, please go ahead and bring those up in the chat, and I will get to them as they come. So Van, you showed the setup ratio in terms of the total capacity. Do you think it's more appropriate to look at the setup ratio in terms of just the shaft resistance? I mean, your example was showing how it's not that great to incorporate the total capacity for a setup ratio. If you follow what I'm saying.
I do know what you're saying, and I'm not a fan of, except for in a drivability analysis where you're trying to see if you can get a pile to penetrate a layer or what size hammer and section you need for initial drive, and you're doing that at the drivability analysis with a wave equation. I'm not a big fan of setup ratio at all. I don't know how to incorporate it into driving criteria well. I mean, it's one thing if you have a very consistent site profile. Everywhere you're driving piles, the stratigraphy is the same. You're going to stop them, say, at a hard layer, all at the same depth, and you can ascribe a uniform response for every pile across the site. Most of my experience is not in those geologic conditions. So I always think of it in terms of variability, spatially and depth-wise. And so in order to apply a setup ratio to a shaft resistance, you need to know the shaft resistance during driving so that you can ascribe what it's going to be long-term. And I don't know how you do that during driving unless you consider all your driving conditions everywhere on the site to be uniform. And I think that driven piles are more flexible and can be put to better advantage on variable sites than that. So
Mhm.
I don't know if that answered your question, because I'm not a big setup ratio fan, and other than with respect to drivability in any application.
Okay. Someone, an attendee asked about, they're saying that in the setup graph, there was a layer that showed, that was labeled as fine grain cohesionless soils. And the question is, that was a silt layer?
Could have been silt. I won't take everyone's time to go back to that slide. I think that am I correct in that the attendees will receive copies of the slides or have them available?
They will definitely have a copy of this presentation will be
Yeah.
available. Or,
Yeah, so you can
yeah.
go back and look. Generally fine grain, yeah, cohesionless means silts or fine sands, silty sands, even just clean fine sands, something like that. Yes.
Okay,
I see a couple other questions. Can I jump in here,
go ahead.
Travis? How reliable is the capacity ratio between the shaft and the toe? In other words, how reliable is the calculation of toe capacity versus total capacity from dynamic analysis? Okay, I'm going to take that a little bit further. First, I'm going to talk about the calculation or the distinction of toe capacity versus total capacity from static load testing instrumented with strain gauges, because we've talked about that in the presentation. That gets very tricky because the to reduce the strain data, you need to know the composite section modulus, and to do that, you need to know the elastic modulus of concrete, and that's not well known or estimated. And so as you get lower in the pile, your certainty of or your estimation of internal forces from strain gauges lower in the pile, that is near the toe, become less certain. So that becomes a little bit uncertain, a little bit problematic to separate it with static load testing alone. Dynamic load testing, now this is more in Travis's expertise, so I will comment and then ask if he needs to correct or add. But the harder the driving, the harder the dynamic analysis, the harder time the dynamic analysis might have separating toe resistance from the shaft resistance on the lower couple segments. Segments are generally on the order of 7 feet. So a dynamic analysis and a subsequent signal matching, like a CAPWAP, might have trouble distinguishing the resistance at the base of a pile, whether it's on the last few shaft elements or on the toe. Travis, did you want to add anything to that?
No, what you said is accurate. I mean, you're certainly relying on the capabilities of your evaluator to differentiate between shaft resistance and end bearing, which is why there's maybe some requirements of qualifications of the engineer doing that analysis. That's about it.
Okay. Another question. While this presentation used proven setup, do you have an upper time limit when projecting / extrapolating setup into the future? The Paul Bullock paper alludes to a limit of 90 days. And yes, I'm familiar with the Bullock paper. And I think Felinius actually has some setup measurements out to a year or more. In theory, soil mechanics theory, consolidation theory, setup and consolidation and excess pore pressure dissipation continues forever, right? I mean, that's why in consolidation, you look at a T90, 90% dissipation, 90% consolidation. Theoretically, setup would continue due to excess pore pressure dissipation forever. And there are other mechanisms that come on after excess pore pressures may have been considered to dissipate, say in granular deposits where the pore pressures do dissipate fairly rapidly. There are things like calcareous cementation and arching and thixotropic strength gains, aging, things like that. So I would say that it's very dependent, again, on soil type, pile type. It probably does continue beyond 90 days. Here's what my personal practitioner practice was. I don't extrapolate setup. If a client doesn't have the time or money or inclination to test for setup, then they don't get to use it. I'm not, it's the client's benefit at my risk if I extrapolate setup. as a practicing geotechnical consultant, I would not go there. If you test setup at 40 days and you get a straight line like we showed, linear with respect to log, and you say, well, you can extend this out. I don't. You tested to 40 days, you get the setup at 40 days to use on your project. End of story, in my mind. But theoretically, it continues forever.
There's another question that sort of think just rolled into your response, actually, right?
Do we need to mobilize or prove the setup gain by restriking? Is that what you were referring to there?
Yes.
Yeah, definitely. I mean, that's the only way. That is, you're right, Travis. That is a direct roll into my last response. If you haven't demonstrated it, at least I personally, because again, I practice in an extremely variable geologic setting, non-uniform conditions at all, not at all. I had a couple of projects 3 blocks apart. You would take the soil borings from those 2 projects 3 blocks apart, put them next to each other, and you would swear that those soil borings were drilled next to each other. The soil conditions were virtually identical. And yet 3 blocks apart, the setup measured on one site was 3 times the setup measured on the other. So I don't ascribe anything that I don't test for. I don't ascribe in design.
So Van, can you explain a little about how you see setup at the toe? What is the mechanism that you have set up at the toe? Because I know that I've heard you say that you do see it in some instances, and I agree with that. But how does that setup occur?
That's a good question. I think it's similar mechanisms. I mean, you get excess pore pressures generated below the toe as well, right? It's not just due to shearing or disturbance or soil moving aside as a displacement pile pushes through the soil, and then adjacent to the shaft, that soil is all mixed up and disturbed. But you've got a, if you picture the log spiral failure wedge below a spread footing, that's what's happening below the pile toe. You're getting a failure wedge below the pile toe, and there's disturbance happening there, and therefore pore pressure is building up as well. But generally, that area is so small, and the change is so small. And except in the cases of relaxation, it's conservative to ignore it. So it's not generally characterized. And again, that's very depth specific. It's not like a cumulative shaft setup profile where you can say depth wise, here's the toe setup we expect. You can only measure toe setup at end of drive at one depth.
Yep.
And so it's hard to incorporate it into a depth variable criteria when you only have that answer at one depth. Did it answer your question? Is that
it does? It does. Okay, well, we've run over time a little bit, and if anyone has some questions, I think they should reach out to Van directly. He's quite can provide really thorough answers to any of these questions you might have. So with that,
thanks again.
I want to thank you again, Van.
No, thanks to you, Travis, for inviting me, to DFI for having me, and for all the attendees for logging in.
Okay. And thanks to everyone for attending. And due to the busy spring, summer seasons, we'll have another sort of long break until our next webinar, which will be July 10th at 2 p.m. Eastern. So mark that on your calendars if you could. And thanks again for attending. Have a good day.